Okay, solving question 36 here. They've given you three enthalpy changes, three equations, and now we've been asked to solve for the enthalpy change in a different equation. So this is Hess's law, the simultaneous equation method. Again, we really just need to focus on these three formulas, and the rest will work itself out. What they're going to be looking for in the mark scheme is that you're doing the appropriate math. So you don't need to focus so much on reworking the equations and showing that work, although you're welcome to use the space to do that. What you really need to show for marks is that you're reworking these enthalpy changes appropriately to get the final enthalpy change. So I need to make sure I have one C2H6 on the left-hand side. If I look up at my equations right now, the way they've given it to me, I have 2. So I need to multiply this whole first equation by a half. I'm going to half all the coefficients, which will half this enthalpy change. So, sorry, I won't erase that. I'm going to multiply it by 1/2. So that looks like it'd be what? Negative 1560. And of course, you'd have a calculator here on paper too. So the type of work you should actually show is that you're going to do 0.5 times minus 3120. Okay, next I want to find C2H4. I need to make sure it's on the product side and there's one of it. I find it here, it's on the reactant side and there's one of it. So I'm going to flip this equation, reverse it. So minus 1 times negative 1411. And then H2, I need one of it on the right. Up here I have 2 of it on the left. So I need to both half it and flip it. So I'm allowed to do 2 things. I'm allowed to do multiple things. So I need to multiply by minus 0.5 for this one. So that becomes positive 280. Oh, I shouldn't make it positive yet. Minus 286. So if I really want to show my work, this is now 1560 negative. This is now positive 1411. And this is now positive, oh, I made a mistake anyways. So this was minus 572. That was showing what I was going to do, and then this is now positive 286. So my positive ones add up to, oops, using my calculator here. So I have 1697 of positive, and I have minus 1560. So I can see the positive ones are bigger than the minus ones, so I should end up with a positive value. And I can see that the difference is 137. So the answer in the end is plus 137. Now, we don't even really need to give units, but we could give kilojoules as our unit since everything here was listed in kilojoules. Okay, then to do the same reaction with bond enthalpies, I need to draw things out. And that's really the trick to bond enthalpy questions, is being pretty quick and careful about figuring out what bonds you have. C2H6, C2H4, missing 2 hydrogens, so there must be an additional bond between the carbons, or else the carbons wouldn't get their octet and their normal 4 bonds. The bonds that we're breaking is 1 C to C bond and 6 C to H bonds. On the right, I've got 1 C to C double bond, I've got 4 C to H bonds, and I have 1 H to H bond. Now, one thing that you can do here, you don't have to do this, but it can make your life easier, is if I'm breaking 6 and forming 4, net, that's really like 4 of them just didn't break. Really, that's what's happening. 4 of the bonds are staying in place, right? It's really only these 2 that I have to break. So I can just not even deal with that, and I can cancel that down to 2. And then I just go use table 11. The C to C bond is 346. The C to H bond is 414 times 2. So 346, 2 times 414. Wait. 2 times 414. Forgive my calculating. Okay, so 1174. This is the type of work that we would want to show to make sure we could earn some partial credit. The C to C double bond is 614, and the H to H single bond is 436. That adds up to 1050. Okay, so I can see this is the energy I'm putting in, that's positive, and this is the energy I'm getting out from forming, so that's minus, And then the difference is looking like it's going to be 124, also positive, because the energy in is greater than the energy out. So this is also in kilojoules or kilojoules per mole. And they said suggest with a reason why the values obtained in part BI and BI4 are different. Well, they're probably different, most likely because bond enthalpies are averages. So bond enthalpies are not specific to these compounds and this reaction. It's only a 1 mark question. That's probably totally valid. Everything is in the gas phase, so it's always a good idea to look at the state of matter also, especially with bond enthalpies. But if in one of these reactions they'd listed one of these things as liquid and the other one gas, that difference could be because we're dealing with different states and we haven't taken into consideration like condensation or vaporization enthalpy changes. But in this one, all the states are the same, so it must be that the bond enthalpies are averages and not specific. The bond enthalpy one is probably the less accurate one, and the Hess's law one up top is likely more accurate. Okay.